Hey, welcome back to the Kibber Data Science channel. This is the afternoon of, evening of Wednesday, January 18th. We're going to continue tonight to work on the Quant, what's it called, World Quant University Data Science Lab. We're moving on to section 022 this evening, so sit back, relax. Get back with you folks in like 15 minutes. Oh, hey, Stephen, how you doing? What are you up to this evening? I'm going to begin to work on the second chapter of the second module of the WorldQuant University. Good. I'm working on learning some SQL. Right. Good stuff. Good stuff. I got a website for you. Of course, you know about what's it called, the GPT, amazing resource for SQL and everything else. But anyway, here you go. Bookmark that site because I use this site all the time when SQL. As you can see over here, it has command summaries, function summaries for all these different databases. Okay. Yeah. So like I said, I use that this site all the time when I'm on SQL. But anyway, tonight, I guess maybe a week ago, someone mentioned a site called the World Quant University. Okay, here it is. It has two courses, Masters of Science program, and this I'm doing the Applied Data Science Lab. All these offerings are completely free, completely free. Okay, uh, I'm on the second. The program consists of eight modules. Each module contains maybe 5 or 6 lessons, and I'm on the second module, the second lesson of the module, on this module we started looking at linear regression models and various ways to do feature engineering and get a handle on apartment costs in Brazil. Okay. Oh, it's very good. It's very good. The instructors are good. The codex exercises are very good, and it's completely free. I mean, if you and it's all Python based so far anyway. But I think it's all Python based. If you're looking to learn some Python, this would be a very good place to start, even finish. You do get a certificate at the end for what that's worth. But yeah, so I've been taking a few notes over here. Just really two. Must be on 2.3 then. Oh, so we're starting a new section over here then. Yeah, so we're beginning 2.3. Yeah, there is an application process. You actually have to pass a quiz, but if I pass the quiz, you can pass the quiz. You sign up, you take the quiz, and bang, you're in. Okay. So anyway, we're on uh, we're on 2.3. Where are we on 2.2? I can't remember now. Now we're on 2.2. Right. Make sure this is right. And I've been kind of keeping notes of all the various sections. So we are on to 2.3. Create new file. Okay. So what you have here is you have a series of lectures, a series of lessons. Each lesson generally includes a 5-minute video. One thing that's good about a lot of the sections repeat themselves, so that way you get to use the various functions and multiple times. So what I do, let's come over here. Now you can use, so this is GitHub, okay. In the back ticks it just says keep the formatting the way it is, okay, the way it's entered. Now I've done a fair amount of mid-level uh, R programming in the past. I've known SQL for like 20 years, but I finally decided to break down and since this looks like a really good option. Uh, so far we've tried to predict the price based on the uh, the size of the property as a first linear regression model. Then in the last chapter we tried to predict the apartment price by longitude, by its location, longitude and latitude, and it comes as no surprise that the closer you get to the waterfront, the more expensive property gets. Okay, I'm not using an elaborate system here. So let's take a look at this first video. Are you learning SQL as part of your job, or is this part of just to be doing on your own? Oops. Run this first section to load our libraries.
Okay, you made it to lesson 3 of Project 2. So welcome, here we are. Let's get started. I'm going to pull up the presentation for today just to give you guys a sense of what we're going to be doing. This time, or rather, let's start last time, we were looking at location in terms of latitude and longitude and seeing the influence of those two factors into the price of an apartment. Today, we'll be using another measure of location, but this time it's going to be neighborhood. So how does neighborhood influence home price? Or how can we use neighborhood to predict home price? In terms of our goals for today, the first thing we want to do is we want to build a model that's going to predict apartment price based on neighborhood. So again, another way to get at the question of location. The other thing that we're going to be doing is, since we're dealing with neighborhoods, latitude and longitude, that's a continuous variable. But neighborhoods are categorical. You're either in a neighborhood or you're not. And so we're going to have to talk about how we can encode this categorical data in order to train our linear model. And then the other thing we're going to have to do, and this is something you will face as a data scientist day in and day out, is we're going to have to battle overfitting. So what happens when our model doesn't generalize? And we'll battle overfitting using something called regularization. So those are our 3 goals for today. Okay, let me give you some highlights for what we're going to be doing today. And remember that we're following a machine learning workflow where we start with preparing data, then building our model, and then communicating results. So in that first section, preparing data, the new things that we'll be looking at is when it comes to importing the data, we'll be using our wrangle function together with a for loop to import multiple CSV files at the same time. And then in exploration, we're going to see that we need to do a little bit of cleaning of our data set in order to extract the neighborhood information from our data. The next part of the ML workflow is building the model. And here, the new areas we're going to focus on are during iteration, we're going to learn how to use a one-hot encoder to encode categorical variables so we can train our model. And then when we get to evaluation, we're going to see what overfitting is or how it manifests itself when you're evaluating your model. The last part of the ML workflow is communicating results. And here we have a couple things that we're going to focus on. First, we're going to look at the curse of dimensionality. So what happens when you don't just have 2 dimensions or 3 dimensions when you're plotting your data or building your model, but many, many, many more, and how that can mess with model performance. After that, I want to talk a little bit about regularization, that thing we use to battle overfitting. And specifically, we're going to look at a new type of linear model, so not linear regression, but ridge regression. And then finally, we're going to, since we're going to be dealing with multiple dimensions, we're going to look at a bar chart, so a way to visualize our coefficients when you can't just fit it all on a single equation in the screen. Before we dive into preparing our data, let's just look at the different libraries we're going to be working with. Let me appear myself here. So some of these are going to be familiar to you. For example, warnings, to filter out those warnings. After that, we're going to be using glob. And glob is a great library you can use. It comes with the Python standard library if you want to search for files that follow a certain pattern. We'll see how to use that in a little bit.
So are you a data analyst, data scientist right now?
After that, we have matplotlib for visualizations. We have NumPy for a little bit of math work. We have Pandas for data wrangling. So all good friends of yours by now. After that, and this is one I want to draw your attention to, and in fact, let me just zoom in so it's even easier to see. We're going to be using a new library called category encoders, and we'll be using the one-hot encoder class from that library. So note that scikit-learn has its own one-hot encoder, but in this case, we're going to use the one-hot encoder that comes with category encoders, just because it's a little bit easier to use, in my humble opinion. After that, we have a bunch of scikit-learn friends, which we know very well. We have the simple imputer. After that, we have linear regression. And then that other model that I talked about, ridge regression, we're importing that as well. In addition, we have mean absolute error for evaluating our models. We have make pipelines for making the pipeline that will be our model. And then check is fitted just to check our work as we go. And last but not least, this is just a little bit of code to suppress those future warnings. All right, well, those are our friends. Now let's get to work with prepping our data.
Okay. So we ran all this up here. Let's make a note over here that nice. That sounds pretty. That sounds like quite a bit. How long you been in the? Have you been here before? The Salesforce administrator sounds familiar. Have you been here before? Okay. Sorry to recognize your name, but I recognize your job title there. Okay. So let's go ahead and load up our stuff here then. And down there's our function call. And so this function, which we've been kind of building all along, does a little bit. Pulls out the records it has capital Federal in the parent names, pulls out apartments less than 400,000, and then it comes down here and splits out, calculates a quantile, and it also then it takes this and creates a new thing called mask area, which contains low and high. And down here we finally split out the longitude latitude columns. So we got that, right? So now we got 231 here. Use glob to create a list that contains the file names for all the Buenos Aires real estate files in the data directory. With quantiles is a statistical function. It one place if you ever seen at a box plot, a box plot is a visualization of a quantile. Quantiles represent, if I understand this correctly, a portion of the of a data set. Okay, so it's not, and so if you have a 25% quantile, that means 1/4 of the data is below that line. Okay, the 50% quantile or median quantile means a 50% of the values, not the values as numbers, but just the number of values there are, regardless of what they are, below that line. 75%, and of course 100%. No. Uh, let's see, what can we do up here? Does it return a Boolean array? No, I don't think so. It returns numbers. It returns integers. Okay. And any outliers would still be there, which is why you use a box plot to see the outliers, and also a histogram. So we go use this last lesson. We use Wrangle for two CSV data frames. But what if we had hundreds of CSVs to import? Wrangling them one by one wouldn't be an option. All right, so we're going to come down here then.
Okay, time to prep our data. So let's start with importing. And you can see here that we have a big old wrangle function. Our wrangle function is getting bigger and bigger. And what we have in it so far are the things that we built over the last two lessons. So we have the code that allows us to subset to the subset of apartments that we're interested in. We remove outliers here. And then we also clean up the lat long column to make the separate latitude and
Let's see. Okay. Uh, yeah. In this function here, we used the quantile function to get rid of outliers. So we're only taking the place from the 10% quantile to the 90% quantile. So anything outside it, we consider anything outside of this here, okay, to be outliers.
longitude columns. So let's just start off by hitting Shift and Enter and getting that function into memory. In the previous lesson, we used our wrangle function to import two CSV files, and we did it one at a time. Now, the wrangle function was very helpful in the sense that it automated that cleaning process, but imagine if instead of two CSV files, you had 200 CSV files. It would be a real pain in the tuchus to import them one by one. And so, even with a wrangle function, right? And so what I want to do now is show you how to use a tool called glob to import multiple CSV files at the same time. I'm going to go here to the notebook, and in the file picker, I'm going to go to the data folder just to remind us that here, all of the data for this project is stored in 5 CSV files. And all of those CSV files have a similar naming pattern in the sense that they start with Buenos Aires real estate and they end with .csv. And the only difference between them is that one numeric character, right? So what we want to do is we want to write a bit of code that will allow us to grab that pattern with not worrying about the little variations in that pattern. And the way that we are going to do that is we're going to use glob. So if I zoom in here to the code, I'm going to start with glob, which I imported up above. And inside glob, I'm going to create a string. And that string is going to be the pattern that I want it to look for. So I'll do Buenos Aires, a real estate, there we go. And then a dash. And then for that part of the naming, the name that I want it to kind of say, it could be anything, I'm going to use this asterisk, that little star operator. It's basically as a wildcard. And then I'll end with .csv. There we go. And if I run this bit of code, we can see that what is returned to me is a list, and the list, the
Hmm. Excellent. Okay, good.
items in that list are all of the files that match that pattern. So what I now have is I have a list of all of the files that I want to import. And I can use that for importing. So let's move to the next task and see how that works.
So let's just test our logic here. That's good. What's a for loop? What's a for loop in Python? Hmm.
For this task, I want to take all the file names that I've saved in files and use that to import all of the CSV files into data frames. So we're going from file names to data frames. Let's see how that would work. I'm going to zoom in here, and I think the best way to do this would be a for loop. And the way I'm going to attack this is I'm going to start with an empty list called frames. And this is where I'm going to store all the data frames as I read them in from the CSV files. And let's create our for loop. Let's do it like this. I'm going to do for file in files. All right, so for file in.
No. Nope. They have no idea whether you're working or not. You don't ask. Well, I can't remember if that's true or not. No, but I don't think it makes any difference. I mean,
files, and let's just quickly remind ourselves what's happening. So as I iterate through this for loop, it's going to go one by one through all of these file names. And what I want it to do is I want it to read those files.
Just go over there and sign up and see what happens.
Into data frames. So the next step would be to remove this print, and instead, let's create a data frame. We'll do df equals, and this is where we'll use our wrangle function. So we'll do df wrangle file. Beautiful. And in fact, what we could do here real quick is let's just do print df.shape just to see that it's working. So I'll do df.shape. Let's see here. And I'll do Shift and Enter. And we can see here are my 5 data frames as they're being read into, or my 5 CSV files as they're being read into data frames one by one. We can see that they all have around 1,300 rows. And so I have all of these data frames. And what I want to do is I want to put them into that list that we created, that empty list, that frames list. So what I'll do is I'll do frames, and then I'll do dot. Do you guys know what it is? I bet you know. Think about it. Think about it. It's append. So I'll do append, and I'll say append this data frame. All right? And if I hit Shift and Enter, actually I'm going to do Option Enter to create a new cell down below. And let's just take a little bit of a look here. So look at frames. Frames is a list, and we can see that in frames, if I put in the correct name, that's why I'm getting that name error. If we look in frames, I can see.
Well, it's called frames. Let's come here. Let's add a new frame. And he's saying let's do a len on the frame. Five, good. What about shape? Let's just do a shape here. How about okay. So we can come over here.
That I have 5 items in it. And if I look at the first item here, so I'll do frames 0, let's see what the type is, the type, and we can see that it's a data frame. And if we look at the first item here, if we do dot head, we can see, aha, here's that first data frame that we know so well from the previous 2 projects. Remember that index 4929? Well, here it is. And so now what I have is if I can just zoom out here, I have a list, and inside that list, I have my data frame, data frame, data frame, data frame. All right? So now I have them all in one place, and the last thing I need to do is concatenate them.
We didn't do a concat here. Yeah, and this is basically how the whole all lessons set up. You get a little bit of you get a 5 or 10 minute video followed by a couple programming exercises. Let's go over here then. Concatenate the data frames.
Okay, so we have our list called frames, and inside that list we have 5 items, and all of them are data frames. So we have a list of data frames, and what we want to do is we want to concatenate them together. So the way to do that is the same way that we did it in the last lesson. I'll do pd.concat, and then inside I'll put frames, which is a list, so I'm good to go. And then, of course, we also need to do ignore index, and we'll set that to true. So if I hit Shift,
That's square brackets or round brackets. Frames. Ignore equals. But let's do this. Let's do a shape first of all. So we now have 6,582 rows and 17 columns. Okay.
and enter, what we now get is our brand new fancy data frame with how many items do we have in it? We now have 6,582. And if we run that through our assert statement, it looks like we're good to go. So now we have all our data in one data frame, and it's time to begin exploring.
Now it's time to do some exploring. All right. Check our code here. Yeah, very good. Excellent work. Now you can now clean and combine as many data frames as your computer can handle. Let's go back over to, let's go back over here to explore now. Looking through the output. Hey, okay, how you doing? What should I call your friend? I him? Elim? Thanks for stopping by. I appreciate it, friend. What have you been up to since I saw you last? We're working through the WorldQuant University's data science lab. Uh, I'll say again, this is a completely free course. Isla, Lola. Okay, maybe that does sound familiar. So you've been here before? I'm sorry if I forgot your name. My short and medium term memory is a. Hey, you and Stephen both are trying to use SQL. Yeah. Did I give you any links to any of my favorite sites on SQL last time you were here? Oh, okay, I should remember that. Yeah, yeah. So what's going on in your neck in your part of the world today? Where I am on, as I say, if you're interested in learning data analytics, I highly recommend this course. First of all, it's a really solid course. Second of all, it's completely free. You know, it's completely free. That's what they say on the site, and that's my experience. Okay, so I'm now on the third, the third of 8 modules. All right, the third of 8 modules, and the and the and the third lesson of the second module, or the third module, or maybe it's it's the second module. Anyway, so we're on task 2.3.4. We just wrote some very brief code up here to read all 5 of our files in at one time and combine them into a single data frame down here. Okay, let's just see what this rascal has to say here. Then for explore. So next we have to extract the neighborhood feature. Okay, create a neighborhood feature, whatever that means. So have you done any SQL work this week since I saw you last?
Okay, we've done our importing and now it's time to do some exploring. Now remember that we want to make our model, we want our model to predict apartment price based on neighborhood. So the main thing we're concerned about is that we have that neighborhood information in such a way that we can actually build a model with it. So let's see if we have that. This is a good time to do some exploring. And the neighborhood information is here in the place with parent names column, right? So all of the information we need is, in theory, right here. Now, what is the problem? Well, the problem is that if we look at these individual strings, we can see that there's a lot more in there that we actually don't need,
Oh
right?
yeah,
It has
yeah,
the
yeah, yeah.
country, Argentina. We know everything.
Alex is a good guy. Yep. Did I give you Data Devs? Did I give you a link to Data Devs YouTube channel? I'll give it to you again just to make sure. There's actually several good SQL channels out there. Data science tutorials. Where's that guy at? You got stuff like Essential SQL, which I haven't watched much of. Dr. Dave, Workout Wednesday. Or it's called the bearded data, bearded dev. Yeah, this guy here has quite a few good videos on more intermediate to advanced functions in R. Yeah, that's Stephen. You can also take Stephen. You can also take a look at this guy's YouTube channel also. So Lola, did I give you a link to techontheweb.net? Tech on the website.
Is in Argentina. It has Capital Federal, so telling us it's in Buenos Aires. And really, all we want out of this column is we just want this last little bit of text, these different neighborhoods, right? Chacarita, Bieluro, etc. So the question is, how do we extract that information to create a new column called neighborhood?
Let's just take a look here. Let's just take a look here again. Okay. And of course, most important of all, never overlook that chat AI. Suppose there's even some better AI clients coming down the pike also. Now here's the thing. So for the last thing is the neighborhood. We could do a split based on the bars, which would give us 1, 2, 3, 4, 5. But we'll see what he's going to do.
Neighborhoods. Let's clear this, and I'm going to scroll down here to where we have our next task. And let's create a new cell and do a little bit of experimenting before we put this into our wrangle function. So if I zoom in here, there we go. The column that we're interested in is, what was it? Place with parent names? Place with parent names. There we go. Dot head. And remember, this is an object, all right? So this is a string. So what do we need to do when we need to kind of split a string? Well, we're going to use .str.split. And in this case, we're going to want to split on that vertical bar.
Go.
And if we do .head, we can see that this is looking pretty good. So here we have our lists, and we just want to grab this last item. Why don't we do the following? Let's do our expand equals true, like we've done before. And so we no longer have a list. What we now have is a data frame.
So what do we say here? The parent name dot That's interesting. Hang on a second here. No wonder what the devil was doing wrong there. Aha. So we're interested in three, right? Three is the name of the city, name of the neighborhood. So anyway, Lola, what this is the third uh, session in a row I've been working with various types of linear regression models. We did things like build a regression model on price and the size of the property. We did try doing on price and longitude and latitude. Didn't work too well, although it did appear that cities properties closer to the water to the shoreline as more expensive. Now we're going to try to do analysis based on price and the neighborhood it's located in. And so what this last uh, thing is, as you can see, this is a place name, place with parent names. It's country, city, capital federal, and the neighborhood name. Okay.
And in this data frame, the column that we are interested in, there we go, the column that we are interested in is this column that's been given the label 3. And so if we want to just have the neighborhood information, what we could do here is, let's see, we could just use square brackets, like we're accessing a column in any data frame, put a 3 in there, and then bada bing, bada boom, we now have all of our neighborhood
Bada bing, bada
information.
boom.
So what I can do is, let me copy all of this.
All right. There we go.
And let me zoom out, and I'll scroll up to our wrangle function. Isn't this fun, scrolling? All right, beautiful. And then we need to add to our wrangle function here. So let's see here. We'll go extract neighborhood. Neighborhood. There we go. And we want to create a column, so we'll
So we're moving this bad boy back up to the top there, are we?
we'll do df, we'll call it neighborhood. There we go. And let me zoom in here. We'll paste in the code that we had before, and we can use df here because df is the name that we're using locally within this function. The only change that we want to make is we want to remove this head because we don't want the first 5 rows. We want everything. Beautiful. And then the last thing that we definitely need to do is df drop. We're no longer going to need place with parent names, so we can just drop that column. So I'll do df drop columns.
All the way back up here to our code. I before E except after C. If I can spell neighborhood. Remember, it's I before E, except after C, and in words like neighborhood and way, okay? Make sure we don't forget that. Oh man, I didn't copy it, I guess. Then we want to drop, right? Drop columns.
And then I'll set that equal to place with parent names. And then just like we did above when we were dropping the lat long column, I'll set in place to true. Awesome. Now I'll
Back over to our notes. Okay, let's come back up here, run our code again. Good. Don't know if I actually need to rerun this again. We'll see. Right? Got the data frames.
zoom out and I'll rerun this cell so that our new wrangle function is in memory. And then what I can do is where we did our wrangling,
Hmm.
here where we imported everything, I'm just going to, actually, you know what, there's an even easier way to do this. I'm going to scroll down to our Explore here, to right here, and I'm going to go up to Run, and I'll say, Run all above selected cells. So this will run from the top of the notebook
That's
all the way down to
interesting.
where we are. So it will redo that import.
Well, that's handy.
There we go.
I don't know
And
that.
if I run this cell again, what we'll see is we get a key error because place with parent names is no longer in our data frame. So we know that this worked. And then I can just delete that cell and then run my assert cell here. And since I have no errors, I'm good to go. And so now I have this beautiful data frame. And if I look at df.head, I can see I have this beautiful data frame with this neighborhood column. All right. Well, that's it for our exploring this time. Let's move on to splitting.
So did anything happen at school or work today? I'll be right back. Oh, okay. Back over here. At this point, you should feel more comfortable with splitting data. So we're going to condense the whole process into one task. Hmm. So we should feel comfortable with splitting data. So we are going to condense the whole process down to one task. Hmm. Okay.
All right, it's time to split our data into our feature matrix, big X, and our target vector, little y. All right. So you guys are already, I'm feeling like maybe you're getting comfortable with this. So we're going to kind of combine what we've broken up into multiple steps before. We're now going to combine it into one task. So going here to the notebook, I have two variables that have already been defined. I have my target, so price approximate USD, and then I have my features, and in this case the features is in square brackets, it's a list, and we're only looking at neighborhood. So in order to create my target vector, my little y, I'll do df and then target. There we go, target, beautiful. And then for my feature matrix, my big X, I'll do df features. Beautiful. And if I run this cell, I've now created both the series, that's Y train, and the data frame, that's X train. And if I
Hmm. Right. Mm. Mhm.
hit shift and enter over my assert statements, I can see that they passed. And so now my model is split, and I'm ready to start building.
Hmm. Ah, yes, the old baseline. Now, the problem here is, of course, is that We're dealing with categorical variables. Neighborhood is a categorical variable. Mm-hmm. Okay, let's see what this rascal has to say here. Baseline model again.
It's time to start building the model. Now, there are going to be some new things in this section. We're going to talk about one-hot encoding, we're going to talk about overfitting, but we're actually going to start with something that should be very familiar or getting familiar for you, which is baselining, right? Finding the baseline performance for our model. So again, we've taken what were multiple steps in previous lessons and combined them into a single step here. Let's see how we do it. I'm here at task 6 and I will zoom in. And the first thing we need to do is create our y mean. So that will be ytrain.mean. There we go. We need to create our list of predictions. So that's going to be y mean times the length of ytrain. Beautiful. And then we have two print statements that we need to fix because they're missing things. So the first part is we need to drop in our mean apartment price. So we'll put y mean right there. And then our baseline MAE, we need to calculate our baseline MAE. So that means we need to use mean absolute error,
Right? Oh, mean absolute error. Hmm. Did I forget something? Do you see anything? Let's just see what happens when he hits
absolute error. And there we would have y train as our first argument, as the ground truth there. And then our predictions, our baseline predictions, the second argument will be y predict baseline. So I'm basically just taking that whole line of code.
And we probably want to put a round up here or something. Mm-mm. Oops, that didn't work either, did it?
And squishing it into that print statement to kind of save us a line of code. And if I hit Shift and Enter, what we see is that this is very similar to what we saw before. The mean price has changed a little bit as we've added more data. Now we have a mean of $132,000. And if we were to guess that over and over again for all of the observations in our data set, we would be off on average by about $44,000, $45,000. So let's keep that in mind as we move into the iteration phase and start building the model.
Mm-hmm. Hmm. What does this mean? What does this mean? When you fit a linear regression model, you're asking the scikit-learn to perform the mathematical operation. The problem is that you are training your training set contains neighborhood information in the non-numerical format. In order to create our model, we need to encode that information so that it's represented numerically. The good news is that there are lots of transformers that can do this. Here we will use one from the category encoders. Okay, the one hot encoder. Hot stuff coming through. Okay, so this rascal. So how far does this actually go down here today? 10, 11, 12. Okay, we still have quite a bit to go then. First, instantiate a one hot encoder named OHE. Make sure to set the user cat names argument to true. Next, fit your transformer to the feature matrix X-train. See what this rascal has to say here.
We're now in the iteration phase, so let's see how we can build our model and maybe what transformations we need to make in order to create a model that can look at a neighborhood and then predict a price. So if I go to the notebook here and I scroll past the instructions, I just want to show you all what would happen if we tried to train our model at this point. Now, keep in mind that our xtrain.head is a list of different neighborhoods, right? Chacarita, Caballito, Once, all right? And so what we have here is text data. This is categorical data that's captured as text, as the data type. And if I wanted to create a model, well, let's see here. If I did model equals linear regression, and then I tried to fit that model, so model.fit using my xtrain and ytrain, what was going to happen? Well, what I get is I get an error here. I get a value error. Now, if I scroll to the bottom of this error message, what it's going to tell me is it's going to say, hey, I couldn't convert string to float, chacarita. So what's happening here? Well, remember that linear regression is a mathematical process. When you fit your model to data, what's happening under the hood is that it's doing ordinary least squares regression, which basically means it's doing a bunch of, matrix algebra. And the problem is that you can't do algebra with words. You need numbers, right? And so our model is saying, hey, I'm trying to do some sort of numerical mathematical process, but you're giving me numbers. So there's nothing I can do. Value error. You're on your own. So what we need to do now is we need to figure out a strategy to take this categorical data and represent it numerically, to encode it so that we can then use it to train a linear regression model. So how do we do that? Well, let me go to my whiteboard here. And right now what we have is a neighborhood column. I'm just going to call this hood to make it short. And in that column, we have different values. So one that we saw was once. Another one we saw was caballito. Another one was chacarita, I think. And so this is what our series looks like. So here's 0, 1, 2. These are our rows. The encoding strategy I want to propose to you guys is one that's called one-hot encoding. So one-hot encoding, or we also sometimes just call it OHE for short, one-hot encoding. So how does it work? Well, what it does is it goes through all of the data here in the column that we want to encode, and it finds all of the unique values in that column and then creates new columns for all of those unique values. So instead of having one column that has once, caballito, y chacarita, what we would now have is 3 columns. So we would have one called once, we would have another one called caballito, which I'm going to just shorten, and then we have one chacarita, which I'm also going to shorten. And then, instead of representing this with text, we can represent it with zeros and ones. So, for example, this row that is once, what I would do is I would put a 1 in the once column and then a 0 in all of the other columns. So this kind of one-hot encoding, this on-off switch, think of it as an on-off switch or as a kind of binary representation of that categorical data. And moving on, for caballito, I would have a 0 for that first column, a 1 for the second column, and then a 0 for the third column. And then the last one, you guessed it, is going to be 0, 0, 1. And so what I do when I do one-hot encoding is I go from that single column, this single column right here with textual data, to a much larger set of columns where each individual value is represented using zeros and ones. All right, so that's the conceptual underpinning of one-hot encoding. Let's see how it works in practice. And for that, I'll need to go back to the notebook. And normally, you would include a one-hot encoder in a pipeline, and we'll do that. But just like we worked with the simple imputer outside a pipeline to kind of see how it works, we're going to do the same thing here, just so we get a sense of how it works. So I'm going to zoom into this code here. Beautiful. And let's begin making our one-hot encoder. So the first thing that I'll do, I've already imported the one-hot encoder class from category encoders, not scikit-learn. And so I'll just do one-hot encoder here. And I know normally I'm keeping everything default, but there's one argument that I always set here, which I think is important to have, which is use cat names, and I set that to true. And we'll see why that's important in a second. So here, with this one line of code, I've instantiated my transformer. The next thing, actually, let's put a little bit of annotation. Let's put some notes here. So instantiate. The next part is going to be to fit. So we need to fit our data, or we need to fit our transformer to the training data. So I'll do ohe.fit, and I'll drop in xtrain. Beautiful. And then last but not least, I need to transform my data. So I'm going to create a new data frame called xttrain, and that's going to be equal to ohe.transform, and we're going to transform our training data. Now, if I can I'm going to scroll up here for a second. Here, let me zoom out, because I want to give you kind of a before and after here. So let's just take this code, and we can remove it here. Beautiful. And let's zoom in again. And so here is xtrain.head. All right, just so we have this in our mind. This is just a data frame that has one column in it, and in that column we have these text values. So once we then instantiate our one-hot encoder,
Hmm. Oh, and there it is. There's a little matrix. Interesting. So the first record has the neighborhood, Villa General Maitre. The next one is Palermo, and so forth. Interesting. Okay, interesting. Good, all good stuff, right? So we use a one-hot encoder to convert the categorical data to numeric data.
Fit it and then train it, we'll have a new data frame, and let's see what we have. So previously we had a data frame that was around 6,500 and one column. Now we have something very different. We have the same number of rows, that same 6,500, but now we have 57 columns.
Yep, there it is, 57 columns, same number of rows, with a whole bunch of extra columns you can see here, okay?
And you can see here that all of the columns are the different neighborhoods. So here's that first neighborhood, Chacarita, here's Luro, here's Caballito, etc., etc. And all of these are represented using zeros and ones. So that first observation, that's in the Chacarita neighborhood, and so it has a 1 there. And then for the other 57 rows here, or 57 columns, it's just 0, 0, 0, 0. So we've gone from a very small data frame,
Yep.
1 column, to a much wider data frame with 57 columns, all right? And so that is how a one-hot encoder works.
I'll be right back in one moment. Okay, hang on a second. We can check this out here. Good. All righty now. Let's see what's so 2.3.8 says create a pipeline called named model that contains one hot encoder transformer and a linear regression predictor, then fit the model to your training data.
Next step is building our model. Before we implement the code, though, let's just kind of visualize what it is we need to do. So we know that our model is going to have a predictor, so I'll put that right here. And we know that this predictor is going to be a linear regressor, so I'll just label that right there. Beautiful. And since our model has this categorical data that we need to encode, we also need to have a transformer. In this case, our transformer is going to be a one-hot encoder. Beautiful. So the one-hot encoder is going to encode the data and then pass it on to the predictor. And since we're dealing with scikit-learn, we're going to take these two components and we're going to package them together into the pipeline that is going to be our actual model. All right? So this is the architecture we're going to follow. Let's keep that in mind, and now let's go back to the notebook so that we can actually, implement it. So going to the notebook here, we need to create our model. It needs to have two components in it. So I'll start with doing a make pipeline, and then what I'll do is for these two curly brackets or round brackets, I will just create a little bit of an indent here so I can put my steps in one by one. The first thing is my one-hot encoder, and I want to be sure to set use cat names to true, and then a comma, and then after that I'll do my linear regression predictor, and I'm going to keep that as default, so no arguments there. So that's me instantiating my model. And then the last thing I need to do is I need to fit my model to the training data. So X train and Y train. Beautiful. And if I hit Shift and Enter, we'll see that that model has been fit and that it has two steps in it. The first step is called one-hot encoder. That's the one-hot encoder. And the second step has linear regression, and that's the linear regressor. So we're good to go. And next we need to evaluate our model, see how it's performing. The first step in evaluating our model is we need to see how it performed on the training data. So let's zoom in here and begin doing that. Again, what we used to do in multiple steps in previous lessons, we've combined into a single step since you guys are now pros at this. So the first thing we need to do is generate a list of predictions. So we'll do model.predict for xtrain. And then we need to calculate the mean absolute error. So that's going to be mean absolute error, and that's going to be y train compared to y predict training. And now I'll hit Shift and Enter, and hey, that's looking pretty good. I've gone from 45,000, 44,000 down to 39,000, so definitely this model is adding some value. Of course, the training data is just half the story. What really matters is if our model can generalize to data that it hasn't seen before, to testing data. So up next, let's see how we do.
Hmm. Interesting, huh? So how do you do that like you did before? Ah, once again, everything ran without error. Yes, this is sort of a trick question. So what do you do if everything ran without error, yet you didn't get credit for the score? Because there's a one question quiz, and this is it for this whole this whole session here. Okay, then there was no errors above. Okay, no errors above. Maybe it's a trick question.
We're in the last section of this lesson. We're in the communicate results section. But we have this little kind of chip on our shoulder because our model that performed so well with our training data, it didn't generalize, Whereas we had 39,000 for our MAE for our training. For our test data, we had like gabillion, zillion, trillion, gazillion, right? A ton. So for some reason, our model is not generalizing well. Now, why is...
Well, so that means that there's nothing wrong with the code beforehand. This is sort of a trick. This is sort of a trick question. So they should give you the opportunity to go back and rerun that question again.
Is that? Well, in this section, I kind of want to focus a little bit on why that might be happening. And it has to do with the idea of dimensionality that we started talking about over the previous two lessons. Now, to get a grasp on this dimensionality, let's go here to the whiteboard. And remember that when we first started with our model, we had price, we had our intercept, and then we started out with just square feet. We had square feet times a coefficient, and that gave us our price. Then after that, we did latitude and longitude. And so our model, we had to add a coefficient to it, another coefficient, right? And we went from 2 dimensions to 3 dimensions. Well, now our training, our feature matrix doesn't have just 2 columns in it. It has something like 57 columns in it. So now our equation is so big that it actually won't even fit on this screen. I just kind of have to abbreviate it here and say, okay, just imagine that there are 55 other terms here. And so this is what my equation is looking like. So why is it important to write out this equation? Well, first, this helps remind us that we're no longer dealing with data that exists in 2 dimensions or 3 dimensions. We're now in a super high dimensional space. And so, for that reason, we often get issues like overfitting and need to do things like regularization in order for our model to generalize well. Now, we'll tackle that in just a minute or two. But for now, the second thing I want to point out is because we have this funky equation, we're going to need to use some different strategies to pull out those coefficients from our model and then display them in a way that's understandable to folks. So first, let's just focus on how do we pull out that intercept and all of those coefficients from our model. I'm going to go back to the notebook here, and let's begin pulling out our coefficients. I'm going to zoom in here, and the intercept and coefficients are going to be very similar to the way that they're going to be identical to the way we did it the last time. So I'm going to go to our model. I'll then use named steps, and then within square brackets, I'll do linear regression, and then dot intercept. There we go, with an underscore. And then for the coefficients, I'll do the same. Same thing, it'll be model named steps, also linear regression, and then dot coef. There we go. I'll hit Shift and Enter. Voila. And we can see here are our 57 coefficients, and here are just the first 5. So we have the values for intercept and coefficients, but what we don't have are the names. Remember, we have 57 coefficients, but we don't know all of the neighborhoods to which they correspond. So the next thing that we need to pull out of our pipeline are the names of those neighborhoods. So let's do that. I'm going to go here to the notebook and then zoom in, and we're on task 12, and we need to get the feature names. So first things first, we'll start with our model and we'll do named steps. But this time, instead of the linear regression, we're going to go into the one-hot encoder. And then, last but not least, we're going to do get feature names. Get feature names. So this should help us get those feature names. And if I do shift and enter, you'll see that the list is 57 items long, so the same length. As the coefficients. And notice here are the names of the neighborhoods. So Chacarita, Villaluro, etc., etc., etc. So we have the coefficients on one hand, we have the name on the other hand. Next step is we got to put them together. So we have our coefficients, we have that list of 57 values, we have the names of our neighborhoods, also a list of 57 values. Now we need to combine them together. If we go to the notebook here, we're going to put this in a Pandas series, which we're going to call featimp for feature importance. And so I'm going to do pd.series, and then inside the series, the data for the series is going to be the coefficients. And I'm going to set the index equal to feature names. And so if we run this cell and hit shift and enter, we can see here is the neighborhood. All right, so here's the neighborhood. This is all the index. And then here are the values. Here are those funky coefficients. So we have our coefficients, we have that list of 57 values, we have the names of our neighborhoods, also a list of 57 values. Now we need to combine them together. If we go to the notebook here, we're going to put this in a Pandas series, which we're going to call featimp for feature importance. And so I'm going to do pd.series, and then inside the series, the data for the series is going to be the coefficients. And I'm going to set the index equal to feature names.
Hmm. Hmm.
So I definitely don't recommend this. I don't recommend sharing this equation with folks, but it is fun to just print it out. Let's take a look here. So what I've done is I've created some code where I'm going to first print out the intercept, and then I have a for loop, and it's going to iterate through that series, and it's going to print out the coefficient and then the feature name. So it's just going to run through that series and print everything out. So if I hit Shift and Enter, we get this long, long list. It's like a laundry list here. We can't even fit it all on the screen. And so this is the equation that our model has determined is the best way for it to predict apartment prices. Although, as we've said before, it's not doing a really good job. And if we look at this equation, I think we can see why the performance is not great. The intercept, the coefficient, these are all very extreme coefficients, very large values, whether they're large negative or large positive values. And so what's happening here is something called the curse of dimensionality.
Here's the problem. We're getting down there close to the end. Will we at some point go back and rerun that thing in order to get the correct score?
So what is the curse of dimensionality? Well, let's give a very soft introduction here. We don't need to go into all the details, but just enough so that we understand what the problem is. So if I have my data, let's say I start with 2 dimensions. So here's my 2-dimensional data. And we can see that there is distance between all of the different points in my data set, right? There's some sort of distance between all of these data points, right? They're not all right on top of each other. Well, what happens is if I add another dimension, all of a sudden those data points become a little bit farther from each other. Now this is 3 dimensions, but as you add more and more dimensions, these data points get farther and farther apart. Now what does this mean for the linear model? Well, when you this is going to be very hand-wavy. I'm going to dramatize this rather than explain it with math. So when you have a linear model and it's trying to fit to data that's in a very high dimensional space, your linear model gets a little crazy. It gets a little panicked. It kind of goes, oh, I want to be as close to all these data points as possible, but I'm in a 57th dimension. I have no idea what I'm doing. And what it will do is it'll kind of shoot off and say, I'll just go to that data point. I'll just go to this data point, right? So it's kind of acting wacky and crazy. Now, what that means for the equation underneath the model is that you get these really extreme, these big positive, big negative numbers as coefficients. So these coefficients start shooting up all over the place, shooting up or shooting down, right? And so that's what happens to a linear model in a high dimensional space. It begins to favor certain data points. The coefficients go all crazy, and then it's unable to generalize to data that it hasn't seen before. And so when we talk about the curse of dimensionality, one of the curses of high dimensionality is that your linear model is going to overfit to your training data and therefore not be able to generalize to your test data. So that's the problem, but what do you do about it? Well, what you do about it is something called regularization. Now, regularization isn't just one thing, it's a whole basket of techniques, and we'll learn a bunch of different techniques, all right? But what it is whenever you have a model that's kind of overheated, acting crazy, it's overfitting to the data, you kind of think about it like this. You're like, hey, crazy model, you gotta act a little bit more regular, right? And what a regularization does is it kind of reins that model back in. It kind of brings it back to normal, All right. And so the particular technique of regularization that I want to talk about is one that you use for linear regression, and it's called ridge regression. Now, the way that ridge regression works, and there's more information about this in the textbook, is a linear model is all about being as close to all the data points as possible. A ridge regression model does that, but it adds a little penalty. It says, I want you to get as close to all the data points as possible, but without having any coefficients kind of be extreme values. So get as close to the data as you can, but keep those coefficients keep them as close to zero as you can. Kind of keep them in check. All right. So that's what ridge regression does. Now, what I want to do here is I want us to take our linear model, I want to pull it out, and I want to swap in a ridge model. You might be saying at this point, hey, Nicholas, slow down. You already tested this data, or you already tested this model on your test data. You've already evaluated it. Once you look at your test data, the model building process is over. You are absolutely right. You're 100% right. Never do this in real life, okay? But in order to kind of show you the difference between the linear regression model and the ridge regression model, I'm going to make a one-time exception, and we're going to redo our model and evaluate it with both the training data and the test data. But just again, I want to underline, you don't want to do this when you're building a model in the wild. This is just an example to get you to see the difference. Okay, so with that in mind, let's go to the old notebook here. Here we are in the notebook. And what I'm going to do is I'm going to scroll up to where we were before, where we actually built our model. Here we go. And then I'm going to zoom in. And instead of linear regression, I'm just going to put in ridge. Beautiful. The next step, if I zoom out, is I'm going to scroll down to where we were before. There we go. And I'm going to just go up to run and do run all above selected cell. So I'm just going to rerun everything all over again. And what you'll see is that if I scroll up here, our mean absolute error for our training data, let me zoom in, is 39,000, so about what it was last time. But look, now our test MAE, while not as good as our training MAE, is way, way closer to where it needs to be, right? It's not way off in the middle of the woods. So we may not have really beat the baseline here, but we definitely solved the overfitting problem. So this is one example with when you're dealing with high dimensional data and a linear model, using something like ridge can help defeat the problem of overfitting. The other thing we need to do is let's just look at the equation to see if any changes have been made. So here, instead of, I'm going to zoom in, instead of linear regression, I'm going to change these to ridge so that we're pulling from the new model we created. There we go, ridge. There we go. We have new coefficients. We can already see that they are a lot smaller than they used to be, right? We used to have plus 16. Now we have plus 3. And if we get the feature names, let's see here, and scroll down to the series, there we go. Again, looking much more manageable. And if finally we print out this equation, and these coefficients seem to make a lot more sense. It definitely is much more logical that being in a certain neighborhood would increase the value of your house by, $10,000, more than that, something like that, but certainly not 10 gabillion zillion trillion dollars. So now our equation, our model is looking a lot better. So what is the curse of dimensionality? Well, let's give a very soft introduction here. We don't need to go into all the details, but just enough so that we understand what the problem is. So if I have my data, let's say I start with 2 dimensions. So here's my 2-dimensional data. And we can see that there is distance between all of the different points in my data set, right? There's some sort of distance between all of these data points, right? They're not all right on top of each other. Well, what happens is if I add another dimension, all of a sudden those data points become a little bit farther from each other. Now this is 3 dimensions, but as you add more and more dimensions, these data points get farther and farther apart. Now what does this mean for the linear model? Well, when you this is going to be very hand-wavy. I'm going to dramatize this rather than explain it with math. So when you have a linear model and it's trying to fit to data that's in a very high dimensional space, your linear model gets
Okay, so just saw a brief article on Facebook. Apparently, a woman in Australia took her neighbor to court. Or she could because of the smell of meat that was coming like from their yard during a cookout or something like that. In response, a bunch of her neighbors got together and they're not having like a block wide barbecue out in front of the woman's house. So it's like I don't think we can tell people to stop smelling, stop cooking meat because someone may not like it. That's ridiculous. Hope the Australian courts kind of like just laughed us one right out of the court. It's really.
gets a little crazy. It gets a little panicked. It kind of goes, oh, I want to be as close to all these data points as possible, but I'm in a 57th dimension. I have no idea what I'm doing. And what it will do is it'll kind of shoot off and say, I'll just go to that data point. I'll just go to this data point, right? So it's kind of acting wacky and crazy. Now, what that means for the equation underneath the model is that you get these really extreme, these big positive, big negative numbers as coefficients. So these coefficients start shooting up all over the place, shooting up or shooting down, right? And so that's what happens to a linear model in a high-dimensional space. It begins to favor certain data points. The coefficients go all crazy, and then it's unable to generalize to data that it hasn't seen before. And so when we talk about the curse of dimensionality, one of the curses of high dimensionality is that your linear model is going to overfit to your training data and therefore not be able to generalize to your test data. So that's the problem. But what do you do about it? Well, what you do about it is something called regularization. Now, regularization isn't just one thing. It's a whole basket of techniques, and we'll learn a bunch of different techniques. All right? But what it is whenever you have a model that's kind of overheated, acting crazy, it's overfitting to the data, you kind of think about it like this. You're like, hey, crazy model, you got to act a little bit more regular, right? And what a regularization does is it kind of reins that model back in. It kind of brings it back to normal, All right. And so the particular technique of regularization that I want to talk about is one that you use for linear regression, and it's called ridge regression. Now, the way that ridge regression works, and there's more information about this in the textbook, is a linear model is all about being as close to all the data points as possible. A ridge regression model does that, but it adds a little penalty. It says, I want you to get as close to all the data points as possible, but without having any coefficients kind of be extreme values. So get as close to the data as you can, but keep those coefficients keep them as close to zero as you can. Kind of keep them in check. All right. So that's what ridge regression does. Now, what I want to do here is I want us to take our linear model, I want to pull it out, and I want to swap in a ridge model. You might be saying at this point, hey, Nicholas, slow down. You already tested this data, or you already tested this model on your test data. You've already evaluated it. Once you look at your test data, the model building process is over. You are absolutely right. You're 100% right. Never do this in real life, okay? But in order to kind of show you the difference between the linear regression model and the ridge regression model, I'm going to make a one-time exception, and we're going to redo our model and evaluate it with both the training data and the test data. But just again, I want to underline, you don't want to do this when you're building a model in the wild. This is just an example to get you to see the difference. Okay, so with that in mind, let's go to the old notebook here. Here we are in the notebook. And what I'm going to do is I'm going to scroll up to where we were before, where we actually built our model. Here we go. And then I'm going to zoom in. And instead of linear regression,
23.8.
I'm just going to put in ridge, ridge. Beautiful. The next step, if I zoom out, is I'm going to scroll down to where we were before. There we go. And I'm going to just go up to run and do run all above selected cell. So I'm just going to rerun everything all over again. And what you'll see is that example to get you to see the difference. Okay, so with that in mind, let's go to the old notebook here. Here we are in the notebook. And what I'm going to do is I'm going to scroll up to where we were before, where we actually built our model. Here we go. And then I'm going to zoom in. And instead of linear regression, I'm just going to put in ridge, ridge. Beautiful. The next step, if I zoom out, is I'm going to scroll down to where we were before. There we go. And I'm going to just go up to run and do run all above selected cell. So I'm just going to rerun everything all over again. And what you'll see is that if I scroll up here, our mean absolute error for our training data, let me zoom in, is 39,000, so about what it was last time. But look, now our test MAE, while not as good as our training MAE, is way, way closer to where it needs to be, right? It's not way off in the middle of the woods. So we may not have really beat the baseline here, but we definitely solved the overfitting problem. So this is one example with when you're dealing with high dimensional data and a linear model, using something like ridge can help defeat the problem of overfitting. The other thing we need to do is let's just look at the equation to see if any changes have been made. So here, instead of, I'm going to zoom in, instead of linear regression, I'm going to change these to ridge so that we're pulling
2311.
And so if we run this cell and hit Shift and Enter, we can see here is the neighborhood. All right, so here's the neighborhood. This is all the index. And then here are the values. Here are those funky coefficients. From the new model we created, there we go, ridge. There we go, we have new coefficients. We can already see that they are a lot smaller than they used to be, right? We used to have plus 16, now we have plus 3. And if we get the feature names, let's see here, and scroll down to the series, there we go. Again, looking much more manageable. And if finally we print out this equation, and these coefficients seem to make a lot more sense. It definitely is much more logical that being in a certain neighborhood would increase the value of your house by, $10,000, more than that, something like that, but certainly not 10 gabillion, zillion, trillion dollars. So now our equation, our model is looking a lot better.
All right, now we get the new feature importance bar chart. There we go.
Okay, so
I realize, of course, all these notes here probably don't make spits. Probably won't make any sense to me tomorrow morning. Anyway, let's see what happens here.
we've fixed the overfitting of our model, but we still can't really be showing off this equation here. It's not really going to work. So the question is, how can we visualize our ridge regression model in a way that makes sense to stakeholders? And I think in this case, we should use something like a bar chart. So let me show you how I would do this. I'm going here to the notebook, and by the way, congratulations, you're on the last task. And I want to create a bar chart. So I'm going to do feature importance. Remember that this is the values where we have the neighborhood and then the coefficient. And I'm going to sort those values. Let me zoom in. So I'm going to sort those values. And I want to sort these values because I want to talk about the most influential coefficients. And it doesn't matter whether they're positive or negative. The important thing is that they're big. So I want to sort these values not from smallest to largest, but rather I want to sort them by their absolute value, smallest to largest. So in this case, I'll set key equal to abs. That gives me a better idea here. And we can see that the largest coefficients are here in the tail of our series. So if I scroll up, I want to just get the top 15 coefficients, the 15 most influential ones. So I'll do tail 15. That'll give me the 15 that I need. And then the next thing I'll do is I'll do plot, since this is a series, and I'll create a horizontal bar chart. So I'll do kind equals bar H. Beautiful. And then a couple other things that I want to add before we look at our visualization. Remember that pandas, we're using pandas here for this first line, but remember that pandas is built on matplotlib. So I'm actually using matplotlib down below to add my axis labels, just because in this case it's a little bit easier. So I'll do x label equals, I'll do importance. And I need to just remind my audience that this is in US dollars. After that, I'll do PLTY label. And that's going to be what? Price? No, it's going to be feature. It's going to be the name of the feature. or the neighborhood specifically. Beautiful. And then I'll do PLT title, and the title for this, let's just do feature importance for apartment price. So we're keeping this a little bit generic. So I'll hit Shift and Enter, and I will just scroll up and hit this. And now we can see this makes a lot of sense. So what we can see here, let me pull out my drawing machine. There we go. So what we can see here is that this neighborhood, Puerto Madero, is associated with an almost 125,000 increase in the price of an apartment, which makes sense. If you know anything about Buenos Aires, Puerto Madero is like the poshest neighborhood. Same thing for a neighborhood like Recoleta. Whereas if you see neighborhoods that are in more kind of working class parts of the city, for example, here in Villa Soldati, you can see that they're associated with a price decrease, or Villa Lugano. So again, what we see here is this model is beginning to kind of make sense with what we know. If we kind of put it into contact with information about the problem, we can see that if you're in a very posh neighborhood, that increases the value of the property, or the predicted value of the property. Whereas if you're in a more working class neighborhood, that decreases the value of the property. Well, congratulations. You made it to the end of lesson 3. Let's think about some of the cool things that you learned this lesson. First, when we were preparing data, we learned how to import multiple CSV files using a for loop. The other thing we did, I don't know if we learned it, it's something we did again, is we were able to pull out that neighborhood to create that neighborhood column using that string.split. When it came to building the model, we learned about one-hot encoding, so how to take categorical data and encode it numerically so that we can use it to train a linear model. And then we also noticed, or we encountered for the first time, the issue of overfitting, where your model performs very well on training data, but when it comes to generalizing to the test data, it doesn't work well at all. When it comes to communication, we learned some new ideas or some new techniques for pulling out all of the different coefficient and coefficient names from our model. The other thing we learned about was the curse of dimensionality, where if you have a linear model in high dimensional space, it kind of doesn't know what to do and it overfits to the data. Now, the way to battle that is to use regularization. And for the regularization we looked at in this lesson, we swapped out our linear regression predictor with a ridge predictor. With asterisk, remember, we did this kind of the wrong way. We looked at our training data twice. You shouldn't do that. But we did see how a ridge regressor can help battle the problem of overfitting. And then, last but not least, we created a horizontal bar chart so that we could show stakeholders what are the neighborhoods that have kind of the strongest, that are associated with the strongest increases or decreases in housing price. So we did a whole lot today, and we kind of built on what we did, and we're going to be using this and building on it for the next lesson. So give yourself a pat on the back for making this, and I'll see you all in the next lesson. Bye-bye.
Okie dokie. Uh-oh. Now we're sticking to stuff with size, location, and neighborhood. There we go. One more lesson, then the end of assignment quiz. I guess you might want to call it end of assignment quiz. All right. With that, my dear friends, I am going to call it a night. And with that, my dear friends, I'm going to bring this live stream to a close.